Hello and welcome to our physical sciences lesson. My name is Tem. Today we are looking at electric circuits. What exactly that we want to understand? We want to look at, the different types of circuits, it could be your series, your parallel, and maybe a combination of the two, and some of the very important reminders in terms of, your current, your voltage, as well as your resistance, right? Okay, so it is within the context of electric circuits. So we'll look at the two types of circuits, which is the series as well as the parallel, and a combination of these two, which is a series parallel circuit. Right, so in a series circuit, all components, right? All components are connected one after the other. This is how exactly you identify a series circuit. So if one component is connected next to each other, then we're saying that it's a series. But also, more importantly about a series circuit is that there is only one path from the positive terminal to the negative terminal of the battery. Now this brings us to something that is also very important. Remember, in terms of convention or by convention, current moves from the positive to the negative terminal. So if there is only one path for current to actually flow, then we actually having a series circuit. Right, so this is how we identify a series circuit. So this is a simple series circuit whereby we have got a battery or a cell. Okay, so all the current passes through the battery, and the amount of current that passes through this battery, or the total current in this case, is 0.5 amperes. Right, what are we saying? 0.5 amperes passes through the battery. Now, if the first light bulb, let's call this R1 and let's call that R2. So this light bulb offers resistance to the circuit. In other words, the two are actually connected in series, meaning that the amount of current that passes through R1 is equals to the current that passes through R2, which is also equal to the total current in the circuit. Okay, so this is a simple series circuit. Right, so in a series circuit, what are we saying? The current remains constant, or it remains the same at all points. So meaning that the current that passes through the cell, okay, is equals to the total current, which is the current that passes through the first light bulb as well as the second light bulb. Hence, we can conclude that in a series circuit, current remains constant. So if we have had multiple components in a series circuit, all of them, we are saying that they will receive the same amount of current. Hence, we can safely say that in a series circuit, current indeed remains constant. Right. Okay, now let's talk something else about, the current as an example. So if we were to connect ammeters at different points in this single path for which current can actually flow, we are saying that we'll get the same reading. This suggests that there is the same amount of current at any point in the circuit. Hence, we say this is a series circuit. Right. What about voltage or potential difference in as far as a series circuit is concerned? So what are we saying? We're saying that in a series circuit, voltage across the battery, right? We can think of this in terms of total voltage, right? Is divided across each resistor connected in series. Right. Let's say, for argument's sake, we had our two resistors, which is light bulb 1, let's call it R1, and light bulb 2, let's call it R2. Right. So we are saying that the total voltage across the battery, in this case, it's very important for us to point out that the internal resistance of the battery, as well as the conducting wires, as well as the ammeter, are quite negligible. So we will not take the internal resistance of the battery into account. So we are saying that the EMF of the battery actually equals to the terminal potential difference, because we are saying that in this case we shall ignore the internal resistance of the battery. So the total voltage in this circuit is equals to 5 volts, right? Okay, so the maximum voltage is 5 volts. Now we are saying that if there is the same current through the battery, through R1 and through R2, we are saying that the voltage is going to be divided. Now, if you check, you'd realize that the voltage across R1 is equals to 3.75 volts, right? While voltage through R2 is equals to 1.25 volts. Now, we come to a realization that the total voltage is split between R1 and R2, right? What are we saying here? We are saying that V total is equals to VR1 plus VR2, right? This is what we mean when we say the 5 volts is divided between R1 and R2. But one other thing that is also very important to note is that R1, is glowing brighter than R2. What does that tell us? It tells us that, R1 has got a greater resistance than R2, okay? So now for the same amount of current, right, we said that current through R1 is equals to current through R2, which is current which goes through the battery, okay, which is equals to the total current. Now, the higher resistance of R1 suggests that there will be greater potential difference across R1, and correspondingly, the lower resistance of R2, there will be a correspondingly lower potential difference. However, if you add 3.75 and 1.25, it gives us the 5 volts, right, which is the total voltage. Right. So in other words, we are saying that in a series circuit, the total resistance is the sum of the resistance of each resistor. So if we had n resistors in series, the total resistance is simply a total of all those resistors that are connected in series. Right. Now, let's look at a branch circuit. Now, the term branched suggests that there is more than one alternative path, in the circuit. Right? While in a series, we only have one. So a branch is what in many ways would refer to as a parallel circuit, but essentially it is a branch circuit which provides more than one path for the current. Right? So a branch circuit forms when resistors are connected in parallel. So a parallel combination of resistors gives us a branched circuit. Okay, so there is more than one path from the positive terminal to the negative terminal in terms of the conventional current. Right, here is a typical example of a branch circuit. Right, now let's say this is R1, okay, and this is R2, the two light bulbs which are connected in parallel. They provide a greater, a more than one path for current. Now, the total current in this circuit, which goes through the battery, is actually 1.5 amperes, right? So the 1.5 amperes is split between R1 and R2, right? So if we say total current is equals to current that goes through R1 plus the current for R2, this will give us the total current. But also very important to note is that the current through R2 is double the current through R1. Now, what does that suggest to us? It says to us that the resistor with the lowest resistance has the most current, meaning that R2 in this case is actually, lesser than R1. Okay, so less current will go through high resistance, okay, meaning that R1 is greater than R2, right? So even if you check here, you'd realize that the brightness of R2 is actually greater than that of R1. Why is it so? There is definitely more current passing through R2 because it has got a lower resistance in comparison to R1. Very, very important, right? So in a branch circuit, current is divided, right? Hence, we would say that a branch circuit where there is a parallel combination of resistors is actually a current divider. So in other words, current is split, because we've got more than one alternative path. Right, so hence we can say that the total current in the branches gives us the main current that passes through the cell. So the current through the cell, would want to also think of it in terms of the total current. Right, so here's a simple example. You realize that R1 is actually half R2, okay? So in this case, if we say this is R1, okay, and then this is R2, all right? We are saying that R1 is equals to twice R2, Okay, so there is more current where there is lesser resistance, but the total current of 1.5 amperes is split between the 10 ohm and the 5 ohm resistor. Very, very important. Okay, so in a branch circuit, current divides, that's a fact, between the resistors connected in parallel. Also, what are we saying? The larger current passes through the smaller resistor. But also, what is important, you know, in a branched circuit is that the voltage remains the same. So total voltage across the battery is equals to 5 volts, right? According to the readings from the simulation. And then again, voltage across, let's call that, just to be consistent, the top one, let's call it R1. So this is R1, okay, that's R2, right? So voltage across R1, okay, is equals to 5 volts, right? And then voltage across R2, again, is equals to 5 volts. So what can we conclude from this branch circuit is that voltage remains constant. So total voltage is equals to voltage across R1, which is also equals to voltage across R2. So voltage remains constant, right? So our voltage remains constant while current is divided, right? So no matter how many resistors we connect or light bulbs we connect in parallel, as long as it's a branch circuit and there are parallel resistors connected, you know, then the voltage across each one of those is going to be constant. So we are saying in not so many words that in a parallel or a branch circuit, voltage remains constant. That's the main thing that we need to take home. Right. So let's talk about resistance in a branch circuit. Right. So in a branch circuit, the equivalent resistance of the branch is calculated using this equation, 1 over R equivalent. Okay, equivalent, sometimes we use the term effective resistance. But remember, we are interested in calculating the equivalent resistance in a branch circuit. So make sure that you actually get the equivalent resistance, not the reciprocal. Very, very important. However, if there are only 2 resistors connected in parallel to each other, we are able to use for only 2 resistors. Okay, this is just a reminder for only 2 resistors in parallel, right? We can use the equation equivalent is equals to product, okay, divided by the sum. This is only applicable for 2 resistors that are connected in parallel, right? Okay. So if we look at the example that we had in the simulation where we had the 10 ohm resistor that was connected in a branch circuit or which is in parallel with the 5 ohms, we can use this formula to calculate the equivalent resistance. You know, R equivalent is equals to the product, okay, which is R1, R2, right, divided by the sum R1 plus R2, okay. So what does that give us? R equivalent, only for 2 resistors, is 10 multiplied by 5 divided by 15. So the 15 is the sum of the 2, right? So our equivalent resistance in this case, there's something that's very important that we need to take note of, right? Then what are we having here? 10 times 5, it gives us a 50, okay, divided by 15. Okay, so our equivalent resistance is 3,33, right? So that's 3,33 ohms. There's something that you need to take note of. The equivalent resistance is actually less than the smallest resistor in this case. So if this is our R1 and our R2 is the smallest resistor, which is 5 ohms. So the equivalent resistance should be below, smaller than the smallest resistance in this case. Right, so that's the stuff in as far as, you know, the branched circuits as well as series. So we'll take a short break for now. When we come back, we'll look at an example of how to approach these types of circuits. See you after the break.